Just let's wait 1 minute the recording. So let's start today's class. I'm just going to, let's finish the time domain structure. It will take about 10 minutes to finish the time domain structure and look at something called as raster. And then we will move ahead. Okay. Okay. So we looked at the OFDM signal generation. It's there in 38211. So essentially until now what we have looked at is we have looked at the time domain structure. We have looked at how the REs and the grid are. So finally, as I told you, it just boils down to, so this is the way they give the OFDM signal generation. It all boils down to one simple thing, taking FFT, and before you take taking IFFT, and before you take IFFT, you have to map the resource grid into the subcarriers in a particular manner. Okay, so you can, I mean, I would expect, I would strongly encourage you to look at this particular equation and see how it can be converted into IFFT. It looks very similar to IFFT, but I would suggest you to do that once. Take a pencil and a paper and just do that. Okay, but I'm going to tell you what is going to happen. Okay, forget about the first sentence. So essentially, what happens is, so you have a map, you have a resource grid. The resource grid is mapped from 0 to capital L. Okay, where L is the maximum number of resource elements that are you using in that grid. Okay, so before you take your FFT, before you take your IFFT, you have to map those things into this part. So essentially, the kth resource, the kth element in the resource grid gets mapped to K bar. Okay, I showed the map here. Okay, for example, the 1638 resource element gets mapped to 0. Okay, and the 0th element gets mapped to 2500. So I'm taking an example of L is equal to 3276 and N is equal to 4096. Okay, and then you give that. So that looks like this. Looks like this. Okay, so this is the input to the IFFT. Once you give to the input to the IFFT, we are done. Okay, if you look at the spectrum, it looks like this. So what effectively happens is, let me just explain you this on a paper, pen and a paper. Just one. Something, just give me 1 minute. I think some technical glitch. Yeah. What this means is, so you have the resource grid. The resource grid elements are membered from 0, 1, 2 up to some capital L. Okay. So let's take an example of capital L is equal to 3276. That is 273 subcarriers, I think so. 3276. Okay. So now you're going to take a 4096 FFT. Okay. Let's take the example of 30 kilohertz SCS and 100 megahertz bandwidth. Okay. So you're going to take a 4096 FFT. Okay. So what is the input to 4096 FFT? 4096 complex numbers, and you take an IFFT and you get 4096 output. Okay. The question is, how do we map this grid to this 4096? Okay. So what happens is, the way it gets mapped is given by this particular equation. Okay. So essentially, the kth element here, the kth the kth resource grid here gets mapped to mod of K minus L by 2 N. Okay, that's what I was showing here, K minus L by 2 N. So this output I call as K dash is the index here. Okay. So for example, the 1638 element maps to the 0th here. Okay, 1638 maps here, 1639 maps here, this will get mapped here.
Okay? Sir, pad is not visible, sir.
Sorry. Yeah. So the 1638, so essentially what I say is 1638 gets mapped here, 0. So because if you take this equation, if I take L is equal to 3276, L by 2 will be 1638. Okay, so it will be mod of K minus 1638 comma N. Okay, so if you put K is equal to 1638, you get 0. Okay, so the 1638 element gets mapped to 0, 1639 gets mapped to 1, 3276 gets mapped to something here, or a 1638 element. Then there will be a lot of gap. Then the 0th element gets mapped here. Then the 0th element gets mapped after the gap. Okay, so that how it gets mapped is what I showed here. Okay, so 0 to approximately 1638. I mean 1638 to 3276 get mapped here, the first ones, followed by a gap, because you can see the height. This is 2500, this is 1600 or something. There's a gap, that gap, and then the next remaining elements get mapped here. Okay, so when you do an IFFT and then you put in a spectrum analyzer, what happens is this gap gets split up into the guard bands on the side. Okay, so what does IFFT do? If you say, if you give the input like this, if you give an input like this, the subcarriers populated like this. Let me do this. Okay, if you give an input like this, so this is the 0, this is 4096. Okay, what it does is 4096 by 2 is 2048 roughly. No, it's 2048. What it does is, this you pass it through your IFFT. Then the final output spectrum would be, this yellow will become the center part. This side it will come like this. Okay. Then the white part, sorry, this part will come this side. Okay, this is how the spectrum will look. Okay, so this is the input to the IFFT. So IFFT, what it happens is the zeroth subcarrier is not the DC subcarrier. The zeroth subcarrier will be, so the zeroth will be the DC subcarrier, but then there's an FFT shift, something called an FFT shift happens. Okay, so this is the output spectrum. Okay, just remember that. Okay.
So is it swapped or half?
Is it swapped? So essentially, what is happening, Roy Sarun? Okay. What is happening is this part is coming here. Okay, this part. So this part is coming here. Okay. It gets effectively swapped. I mean, what you say is swap is correct. So this goes like this. It gets translated to this. This gets translated to this. So this edge and this edge touch each other.
No, so when we are saying swap, it is half portion swapped, or every subcarrier is kind of a swap?
It's half portion swap. So essentially, this whole thing moves this side. This whole thing moves this side. You can see now.
And order of the subcarrier will remain
the
same within that half.
So this subcarrier will come here. This next subcarrier will come here. This next subcarrier will come here. So on and so forth. Okay. Sorry. This subcarrier will come here. This subcarrier will come here. This subcarrier will come here.
So this is not within that half. Subcarriers are not swapped.
No. They are not swapped. They are not swapped. Okay. It's called the FFT shift. Okay. So what you should remember is, in this particular thing, the zeroth subcarrier is the DC subcarrier. This will become the DC subcarrier. Finally, that will become the DC, the center frequency. That will become the DC subcarrier. Okay. So if you now think about this zeroth is mapped to what element in the actual grid? The zeroth element is the 0. This 0 is nothing but the 1638 element in this grid. This becomes a 0 before the FFT, before the IFFT. Okay. So if you are when you are populating the resource grid, you should remember that the 1638 element is the essentially whatever the number of resource elements divided by 2. That half point is the DC subcarrier. Okay, that will be your DC subcarrier. Okay, just remember this. I mean, this is not very critical, but it's good to know this, okay, because this is what finally comes out as a spectrum. Any questions before we proceed?
So when we say DC subcarrier, it will not carry any data.
No. I'm coming to that. I'll just come to that in just this is what you're asking. Yeah.
Okay.
So DC subcarrier. Let's talk about the DC subcarrier. So LTE had 20 megahertz bandwidth, and every user used to support this 20 megahertz bandwidth. Okay. So in that case, there's also beginning of the technology. What they said was the DC subcarrier will not carry any information. They used to null down the DC subcarrier. So, okay, essentially what they used to do is, for example, if you take this 3276 grid, this is a wrong example. They never used to transmit 1638 subcarrier. Essentially, they used to keep it 0. They never used to populate it with actual information in LTE. Okay. In 5G NR, what they said was, see, every user is not going to support the entire bandwidth anyway. We don't know what bandwidth they're going to support. Okay. So there is no point in nulling out DC subcarrier. If you null out the DC subcarrier, that particular subcarrier has to be nulled out in the UV in certain fashion, and that's too complicated. So they said that DC subcarrier also will carry data. Okay. So in 5G NR, the DC subcarrier carries data. Okay. So it's left to the user on how you decode that data. Or if you cannot decode, then you have to use the error correction code and use the beside subcarriers to decode the data. Okay. So effectively, the DC subcarrier does not carry data. It does carry data in 5G NR, whereas in LTE, DC subcarrier never used to carry data. Okay. That's something that one big difference between LTE and 5G NR. Okay. There's one more difference. So essentially, this is what an LTE. Okay, there's one more thing I want to tell you this. Okay. So as I told you before, when we say subcarrier, the center frequency is what we look at. I'm just showing a big example. So this is LTE, this 15 kilohertz subcarrier. So essentially, this is the DC subcarrier was not used. Okay. So what they did in uplink was, so this is the downlink part. In uplink, they shifted the entire resource grid by 7.5 kilohertz. Okay. So when they shifted the resource element by 7.5 kilohertz, the DC subcarrier actually falls between two subcarriers. Okay. So this is the downlink. Essentially, when we think about a subcarrier, what we think about? What we think about is that. So, this is what we think about. Okay. So what they do is the uplink is in LTE, the uplink is shifted by 7.5 kilohertz compared to the downlink. Okay. So that the DC subcarriers fall at the center of the two subcarriers, between two subcarriers rather than the center of a subcarrier. This is something that we have to keep in mind when we do LTE. Okay. So why did they do that? They thought that, see, if there's a DC subcarrier at the center, in the center of one subcarrier, that subcarrier will be completely lost. It depending on which user gets allocated, that one subcarrier is a waste. On the other hand, if the DC subcarrier is a center is between two subcarriers, the effect of the DC will be spread over these two. Okay, that's why minimizing it a bit, so that two users can be allocated. This set of things can be allocated to one user. This set can be allocated to one user if required, or the same set can be allocated to one user, and somehow it gets spread over these two. Okay, that was the idea that they had. So the main important point you have to understand is the uplink will be shifted by 7.5 kilohertz relative to the downlink in LTE. In 5G NR, as a baseline, uplink and downlink are not shifted. Okay, so there is a specific thing called TX direct current location. Essentially, this tells you in which subcarrier is the DC located. Okay, in which subcarrier, if you shift the whole thing, you can also put this DC subcarrier in a specific location. Okay, so the uplink and the downlink are not shifted, but there is an option to shift it by 7.5 kilohertz for the uplink. Okay, for a given bandwidth part, you can shift it by 7.5 kilohertz. They mainly gave this option so that LTE and 5G NR can coexist, and so that this uplink gets aligned with the LTE if required. Okay, so as to reduce interference. Okay, but this is again an option that's given to the user. This shift 7.5 shift dot 7.5 kilohertz. This is a particular UV specific thing. It's particular bandwidth part. Okay, so it's up to us whether we want to shift or not shift.
Sir, this is used in dynamic spectrum sharing. When they share
Yes.
a spectrum, this is how they shift the
between LTE and 5G NR.
Yes.
So as to avoid interference. Okay, so the two takeaway points on the slides are LTE. There's a shift of 7.5 kilohertz. The 7.5 kilohertz shift is a big pain between uplink and the downlink. Whereas in 5G NR, both of them are aligned, and you have an option to shift for a particular user if you require. Okay, again, this is mainly for LTE alignment to reduce interference.
So shift in LTE, is it related to the uplink part where we use single carrier OFDMA? Is that the region somehow?
That is also, you're talking about this slide, sir?
Yeah, in LTE we have a shift of 7.5 kilohertz in uplink, because uplink side we don't use OFDMA, we use single carrier OFDMA. So is that related to that? That since we are using
not exactly. Say essentially they want to spread out the effect of this DC subcarrier on two subcarriers. Okay, so they thought that if you spread it out, if it is in the center, that one thing will be lost. Whereas if you spread it out, see, because you are already allocating only fewer resources to the user, they do not want to miss out one whole subcarrier. What they thought was, the idea was that if this effect was weak, then this center and this center you can decode the data still, depending upon the DC leakage.
Okay, right.
But in 5G NR, of course, this is not. They're aligned, and it's up to us to do the shift if you want.
Okay. This carrier shifting is only for TDD, or it is also for FDD?
FDD. There's no time division, and this is for both.
Both. So it will be shifted not because this is shifted with respect to downlink.
Yeah. So it's shifted with respect to downlink.
It will be different, no?
Yeah. So the grid is shifted. The grid is shifted by 0.5 kilohertz.
Sir, this DC subcarrier is also a subcarrier of 15 kilohertz length, right?
Yeah. So this is also 15 kilohertz in LTE. Yeah.
Then, sir, why only one single line is shown in that picture?
In this, I showed the center.
Okay, that is the center.
The center. See, essentially, what we learned that the center is the one in which there's a sync wavelet that comes now. This 30 kilohertz, 15 kilohertz crossing like this.
Yes,
when we do OFDM. So I generally represent the center. So when we say a particular subcarrier, it's always the center of the subcarrier. You should always remember that.
So by shifting 7.5 kilohertz from each side, 7.5 kilohertz will be affected.
Yes. So this 7.5, this 7.5. So effectively, what they thought was this center might be good, this center might be also good. Depending upon how much DC is there. Okay. The base station, it's much more higher power amplifiers, no? So the carrier will be gone anyway. You can't help it out. But saying that nowadays there are enough techniques to remove all this DC subcarrier and other things, and you can actually use this thing. Combined with coding, you can actually use this very well. Okay. Okay.
Hello, sir.
Ashif, please tell me. Ashif.
Yes, sir. So in LTE, the uplink, the downlink spectral efficiency will be higher than the uplink, lower than the uplink, right, sir?
Why?
If we consider only that block of frequency, so uplink is using higher spectral efficiency than the downlink.
Yeah, this one subcarrier not used doesn't change the efficiency. Uplink has other issues.
Okay. So if you consider consecutive time domain also, so that will not affect.
What is consecutive time domain means? I didn't understand.
So suppose user 1 is allocated time slot 1, time slot 2, time slot 3, something like that, and the whole line of frequency will be omitted for the downlink, so will not be used. But
it will not. No. Uplink is power limited now, so your spectral efficiency will generally be low.
Okay, sir.
Okay. So, but whereas in 5G NR, this DC is there. I mean, say they said this is your headache, how to deal with it. We don't want to specify that in the standard. Okay. So, any other questions? We'll proceed. Okay. So the next thing is I want to talk about the channel raster. Okay. So this is so there are three types of bandwidth. One is the channel bandwidth. Sorry. Okay. One is the channel bandwidth. Okay. Channel bandwidth is the one which devotee gives, which says 100 megahertz. Okay. The other is the transmission bandwidth. Okay. So transmission bandwidth plus guard band is the channel bandwidth. Okay. So transmission bandwidth plus channel bandwidth is the transmission bandwidth plus guard band is the channel bandwidth. Okay. So if you look at the so essentially this is specified in 38103, which is the base station document. It tells you for each subcarrier what is the transmission bandwidth that's allowed in terms of subcarrier, in terms of PRBs, number of RBs, resource blocks. Okay. Both for FR1 and FR2. And how do they compute the guard band is, essentially they say that they take the channel bandwidth, subtract off the transmission bandwidth, and they also subtract one SCS and then divide by 2. That will be the guard band. Okay. So if you forget about this subcarrier spacing, it's exactly channel bandwidth minus transmission bandwidth divided by 2 will give you this half and this half. But what they do is they also subtract off one subcarrier. Okay. And my understanding and my reading of this was this mainly to synchronize with the channel raster. I'm not very sure why they do that. They subtract one additional subcarrier to get guard band. They give a little bit more guard band. Okay. I'm not very sure of that. I mean, the reason I was able to find out was it's mainly to do with synchronization to the channel raster. But I'm not very convinced. I'm trying to find out why that is the case. Okay. Okay. So where is the channel bandwidth specified? So this is the transmission bandwidth. So again in 38103 there's a table which says which band combination has which bandwidth, for what band bandwidth is supported. Okay. For example, if N78, which is a 3.5 gigahertz band, it says for 15, let's just take 13 kilohertz. It says 10 megahertz is supported, 15 is supported, 20 is supported, 30, 40, 50 is up to 100. Whereas 5 megahertz is not supported. Okay. So every SCS and every band, this is a release 15. Maybe in the release 16, some more things became S. I don't know. But in release 15, these are the SS that we have. Okay. So you should see this particular 5.3.5.1 document, table in 38103 to understand what is the bandwidth that is supported by the system. Okay. Is this clear? Okay. Similarly, you have the FR2 channel bandwidth. Okay, so there's something called channel raster. I think most of you know this, but I'm going to explain for the sake of the students. So essentially what happens, you have to see your center frequency can be theoretically be anywhere in the spectrum. Yes, your center frequency can be anywhere in the spectrum. I mean, it can be for, I mean, if you take the sub 6 gigahertz from 0 to 6 gigahertz, your center frequency can be anything, given of course your allocation. Okay, but when you switch on your phone, or when you have, I mean, at least earlier up to 4G, when you switch on your phone, your cell phone should start figuring out at what is the correct center frequency. It can't do a continuous search from 0 to 6 gigahertz. Yes. So what they defined was they defined something called a global raster. Okay. So what is a global frequency raster? A global frequency raster tells that these are the discrete points in which your center frequency can be there. Your center frequency or some reference frequency can be there. Okay. So essentially this is called a global frequency raster. It defines a set of reference frequencies. Okay. They're mainly used to locate the RF channels. This raster is present from 0 to 100 gigahertz. And the granularity, which is defined by delta F, changes for different frequency range. For example, below 3 gigahertz, the raster granularity is 5 kilohertz. So every 5 kilohertz, your carrier can be there. Okay. Whereas from 3 to 24 gigahertz, it is 15 kilohertz. And from 24 gigahertz to 100 gigahertz, 60 gigahertz. So theoretically in LTE and other things, once you start your cell phone, it has to search every 15 kilohertz to see if your carrier is there. If your carrier means your transmission is there or not. Okay, to lock out to the center frequency. Okay, is this clear? Is this concept clear? So this is called a channel raster. Okay, so the channel rasters are actually given by a number called ARFCN. Okay, so yeah, NREF. Okay, NREF. Let's take the NR. I mean, for NR 5G NR, it's called the NR ARFCN. There's given a big range. So what you can do is, if someone gives you a number for NREF, based on this table, you can actually find out what is the reference frequency. FREF equal to FREF offset. For example, at 3.5 gigahertz, your FREF offset is 3000 megahertz. Okay, so you put that there. And the global raster scale is 15 kilohertz. Whatever value of NREF they give you minus NREF offset. Okay, NREF offset is very obvious. No? Can you hear me?
Yeah.
Yeah. Sorry, I did not realize that I put the charger, but was not charging for some reason. Okay. 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 Are you able to? Is this clear?
Yes.
Okay. So, okay, I have to show you a document. What is this? Just 1 minute. Hold on. Okay. So now the question is. So now we have a channel raster. Okay, the channel raster gives us some specific frequency for a carrier. The question is, what resource block and what resource element is it mapped to? Okay, so that is given by so that depends on the number of resource blocks. So it says that the channel raster is mapped to this element. Okay, so in terms of resource block, what resource block is it mapped to? It's mapped to NRB by 2. Okay, suppose you have 272 subcarriers, it will be 356. Okay, 356, sorry. 272 is 136, sorry. 136 resource block it's mapped to. In the resource block, which resource element is it mapped to? So if NRB is even, then it is mapped to 12 into NRB by 2. If NRB is odd, it is mapped to 12 into NRB by 2 by plus 6. Okay. So effectively, if you think about this calculation, the channel raster is always mapped to the DC subcarrier. Okay. So look at my whatever I have written in the yellow thing. Okay. So from a previous slide, OFDM signal generation, where we saw that number of RE by 2 is the DC subcarrier. Yes. So it turns out that the DC subcarrier is exactly equal to 12 into NRB by 2 or 12 into NRB by 2 plus 6, depending upon even or odd. Okay. So the channel raster is always mapped to the DC subcarrier. which is obvious. Now you want the center frequency to be in the DC subcarrier. Yes. Any question?
Yeah, but only one of the channel raster, right? Because every, say you said that every 5 kilohertz there will be channel raster. So one of the channel raster will be DC or?
No, yeah, one of the channel raster, whatever channel raster you picked up. Okay, so let me just let me write it up. See.
So your writing pad is not visible, sir.
Yeah, I'm just connecting it. It got disconnected. Just 1 minute. Okay. So what is a channel raster? Channel raster is just, for example, above 3 kilohertz is a 30 kilohertz grid. Yes. Suppose, so 30 kilohertz grid means you will not be able to get 3.5 gigahertz exactly. Suppose the DOT allocates me 3.5 gigahertz. What I will do is my center frequency will be, if I look at compute the grid, it will be 3.5001, something of this sort, gigahertz. Okay. So I will make this point as my DC subcarrier. Okay. So in the grid, what happens in my resource element grid? This will be mapped to the DC subcarrier. And my spectrum will look symmetric around this point. Okay, around this particular raster point. Ashok sir, does this answer your question?
Yeah. The confusion was that we have n number of rasters, so one of the raster will become kind of DC.
One of the raster point will become your center frequency.
Yeah.
Okay. So essentially, what we have to understand is 3.5 exactly may not be possible. It will be 3.5001 because you have to align to the raster.
Yes.
Okay.
So that's a learning for us that while allocating spectrum, we can also allocate in a way that it aligns, right?
It aligns. But so you will, the alignment will be at most of 30 kilohertz. I don't know if that's,
Okay.
that's something to keep in mind. So in 5G and all, we'll see in another in a class that there's one more raster called synchronization raster. Okay, that's not there in LTE. Okay, so in LTE, what used to happen is, let's get back to this slide. When you switch on the phone, suppose you allocated your frequency band was from 2.3 gigahertz. Okay, so the phone used to search every 5 kilohertz, at least in the beginning, at least 5 kilohertz. Every 5 kilohertz for center frequency. It used to do the synchronization procedure every 5 kilohertz. That used to take a long time. So that's why when you switch on the phone, it takes a long time for the phone to lock onto the network. That's the main reason. Because it actually searches the entire channel raster for the first time. Okay, it will see whether my center frequency is 5, 10, 15, 20, 25 kilohertz, 35 kilohertz, 40 kilohertz. It goes all the way up to gigahertz like this. Okay, of course, you can do something smart there to improve the time, lock on time, but effectively that's what it does. Okay. So then what they did was, so that's what this is a global channel raster. In 5G NR, what they said was this 30 kilohertz is very, very small. So they define some other, so they define their own raster which aligns with the global raster. Okay, so for example, if you take N78 band, they still use the 30 kilohertz raster. Okay, that's called a delta F raster. So each band has a specific raster in which they increment. For example, N38 band has 100 kilohertz raster, whereas the global raster is for N38 band will be 5 kilohertz. Okay, whereas N78 band has 30 kilohertz delta F raster, whereas the global raster is still 30 kilohertz. But N78 also supports, it's 15 kilohertz. The global raster was 15 kilohertz, sorry. The global raster is 15 kilohertz, sorry. Okay. So this delta F raster is always an integral multiple of the global raster, which is greater than or equal to the global raster. Okay. So one thing that, one small exercise that we can, you can do is, if suppose you want to find that, you want to give an allocation at 3.5 gigahertz, we have to figure out what is the closest raster point that's allowed. Okay, so I'm going to give this as a design problem in the homework this time, where you have to tell me what are the raster points, the allocations and other things. Okay, I'll do that. Okay, but you have to keep this in mind. You have to always keep this channel raster mind in for allocation. We'll come back to this example. So I did an example for 3.5 gigahertz. It says that the closest raster point is 3.50001 mega. I mean, 3500.01 megahertz is a raster point, and that ARFC and corresponding to that is 6333334. Okay, and that is exactly the center point. I mean, I'll give you this slide anyway. We'll come back to this and do this in detail when we finish the SSP. Okay, you can look at this. So the takeaway points in this particular thing is, one is the DC subcarrier is used in 5G NR, whereas it's not used in LTE. And there's a global channel raster on which those center frequencies should be aligned to. Okay. And 5G NR specifies its own delta F raster, which are integral multiples of the global raster. Okay. So finally, 5G NR has to be in one of these points, not the global raster points. Okay. Those are the three takeaway points for today. Okay.
So will it always be center of that RB which is coming in between, like after the sixth subcarrier of that RB?
Yeah, so always the center of the RB will be the thing. Okay, so that's why I gave you this thing. So it is, if NRB is even, the zeroth resource element will be taken. Okay, if NRB is odd, then in that NRB by 2, the sixth resource element will be index will be taken. So if you just look at the RE perspective, it's always a center point.
Okay, but if it is even, then it is the first subcarrier where the first carrier.
The first resource element of that resource block.
Okay, that will be the raster point, right?
So I give the raster point here. If this is even, then 12 into NRB by 2, resource element is a raster point. If it's odd, 12 into NRB by 2 plus 6 resource element is the raster point.
Okay. So is it true for all subcarrier spacing, or it is specific to this 30 kilohertz?
It's specific to all subcarrier spacing. No, sorry, it's true for all subcarrier spacing.
Thank you.
On what factors this raster could be dependent upon? It should be 30 kilohertz, 200 kilohertz. So depending upon what it should be decided.
Sir, this is the one. Just let me open the slide. Okay, it depends on the center on your frequencies. So 0 to 3 gigahertz, the delta F global raster is 5 kilohertz. For 3 gigahertz to 24 gigahertz, the global raster is 15, and about 24 gigahertz is 60. But NR also defines its own raster. For each band, they give a raster which is a multiple of this global raster.
So if
tell me, sir.
If a device supports multiple band, then how this will, what step size it will take for synchronization?
So can you repeat the question, please?
If a device supports multiple band,
yes.
What is the step size that will take?
That's an actually very good question. So suppose your device does carrier aggregation of 2 bands. Yes. Then what we do is the primary band, the primary cell band, is what is used for synchronization. Okay, then it will take whatever, if the primary band is in, for example, 22.8 gigahertz, it will take 5 kilohertz, or actually it will take from this table. It will take from this table based on the band that you give.
That is primary component carrier and secondary component carrier.
Primary component carrier and secondary component carrier, exactly.
Yes.
Okay, so it will use this table to find out the raster point. Okay.
The question may also be about bandwidth part, if the phone supports multiple bandwidth parts.
No, sir. This initial synchronization is only to the base station. This is where base station transmits. All the phones have to do this. There's no option.
First, it's required to be synchronized with the base station. That is the only requirement.
Yeah. So this is your base station alignment. Think of this as your base station alignment. Okay. So what the UE, the UE initially, UE can say I will support 20 megahertz, but it has to support the 20 megahertz everywhere. It cannot say I can support only 20 megahertz at 3.456. It cannot do that. It can only say I will support 20 megahertz. It cannot say which frequency it supports. So let's get to the next topic. I mean, this is where we're actually going to get started on the. So until now, what we have learned is we have learned about the time domain and the frequency. I mean, so some things about the time domain structure of the 5G NR signal. We have learned about slots, OFDM symbols, frames, and other thing. And similarly, we have learned about the resource grid. Okay, that's what we have learned till now. So now let's start understanding how this whole system works. Okay, so let's start with this basic thought process. So you are first time entering into the network. There's a 5G network that has been base station network that is there. Your first time entering into the network. You switch on your phone. When you switch on your phone, at that point, you don't know anything about the system. You have zero knowledge of the system. You don't know what is the subcarrier spacing that is there. Okay, you don't know what is the center frequency that is there. Okay, you don't know the band that you have to lock onto. You don't have any idea of the timing synchronization. Okay, you don't know anything. Okay, you are blind at that point. The question is, now I switched on my phone. How do I first of all get some parameters from the network? Yes, how do I get some parameters from the network? So this is the first question that we'll try to answer. Okay, so this is called the initial access. Okay, essentially this thing happens in between also, but what we'll focus primarily is on the initial access when you first time switch on your phone. Think of this that way for some time at least. Okay, so the first thing that you are going to do is you will try to synchronize to the base station, do timing synchronization, find out what is your band, find out the subcarrier spacing. Okay. And understand and try to lock onto the slot and the format and the frame structure. Okay? So to do this, the base station periodically transmits something called a synchronization signal block called SS block. Okay, this is also called SS block or SSB, synchronization signal block. Okay, so this is mainly used by the mobiles to synchronize to the base station. Okay, so at that point, the base station does not know anything about the UV. Only the UV will know something about the base station. Okay, so this is the first step that happens when you switch on your phone. Okay, so this is what we are going to focus in the next couple of classes. We'll understand what is this SS block, how can you use this SS block to synchronize, and what is the information you get from this SS block. Okay, that's what we're going to do. Okay, so as I said, the SS block is mainly used to do cell search. Okay, to initially identify for a cell and then lock on to the network. Okay, so it can also be this same SS block is also used when you're moving from one cell to another. We'll come to that later, but something to keep in mind, the same SS block can also be used. Okay, this is called cell search. So, but when I say initial search, what you have to do is you have to obtain a reference point in both time and frequency on the reference and the resource grid. You have to obtain some basic parameters of the cell. For example, something called cell ID, where something called corset 0 is nothing but the first control information that you have to decode. Okay, it has something called MIB and SIB, MIB and SIB1 messages. It's called SIB1 messages. And what is the subcarrier spacing that you have? Okay, these are the three. What are the subcarrier spacing for the data? Okay, and then you should be able, after you finish this decoding of the SS block, you should be able to transmit something on the uplink to inform the base station that what do you say? Hi, I am there. So please allocate me resources. Okay. So these are the things that are required from this SS block. Fine. Any question? Did you understand the context? Okay. So the first question that we have to ask is, see, one thing that you can say is, why can't the base station just transmit some standard BPSK format data so that the UE can lock on? You can decode that BPSK or QPSK standard formats and then what do you say, understand something about the network. Okay, what is the problem with this? See, at this point you are not even time synchronized or frequency synchronized. Okay, so there's no way you can decode any bits. There's no way you can decode any bits. Even if the base station transmits bits, there's no way you will be able to decode. Okay, so whatever you do has to be based on physical waveforms. Okay, it should say that it's not about decoding it. It's not at the bit level. It's not decoding bits, but it's about understanding what waveform was transmitted and using that waveform to synchronize. Okay. So effectively, what I want us trying to say is this initial block works mainly by understanding what waveform was sent. Okay. So how do we generally transmit information? We transmit information through bits. Okay. If someone gives you bit 0, it means something. Bit 1 means something. Okay. So instead of that, what happens in this particular SS block is they transmit a waveform. If you are able to find waveform 1, it means something. If you are able to find waveform 2, it means something. If you are able to find waveform 3, it means something. Okay. So the information is encoded in what is the waveform that is transmitted, rather than decoding it into bits.
Means waveform corresponding to SSB.
Waveform corresponding to SSB. Okay. I mean, so SSB transmits different waveforms. Depending on the waveform, you have to interpret them in separate sense. Okay. I will come to that. Okay. So you understand why bits are not possible at this point. You will not be able to decode your OFDM frames and other things to get your information. Mainly because at this point you're not synchronized under the system. Okay, you don't know anything about the system. Okay, so this is the initial first lock-on phase of your network, of your UV into the network.
Is there any parameter for autocorrelation factor or cross correlation factor for getting the information or correlating it?
Sir, in a couple of slides this will become clear for you. Okay, so what is the waveforms that they send? Okay, so this is called the synchronization block. Okay, so this PSS and SSS sequences, this was also there in LTE. Okay, but it's a little bit different in 5G NR. Okay, I'll explain you those gaps also. So this is an SS block. SS block consists of PSS, which is called the primary synchronizing signal, SSS, which is called the secondary synchronizing signal, and PBCH, which is the broadcast physical broadcast signal. Okay. So an SS block spans 4 OFDM symbols. You can see this is one OFDM symbol, second OFDM symbol, third OFDM symbol, fourth OFDM symbol. Okay. It occupies 240 subcarriers. Okay, in the 240 subcarriers. Out of, I mean, the PSS is 127 subcarriers. The SSS is 127 subcarriers. There is 8 subcarriers empty on this side, 9 subcarriers empty on the other side. And this is PBCH and this PBCH are 48, and these two are 240 and 240. Okay, so this is called an SS block. So an SS block is a 240 subcarriers by 4 OFDM symbol block. Always remember this. Okay, this is what is called an SS block. Okay, so we are going to use this SS block to synchronize and find the timing information, frequency information, and then decode the basic what do you say?
MIBs, IB also.
Yeah, data about the network. Exactly. MIBs. You will be able to decode the master information block of the network. Okay. It's already 9:50. I'm going to stop there. In the next class, we'll look at what is this SSS, what is this PSS sequences. Okay. How, I mean, I will not give the exact details on the algorithms and other things, how you can decode them, but I'll give an intuition on how you can use SSS and PSS to decode whatever you want. Okay. And then we'll look about the time domain structure of this SSS PSS and how it is used in millimeter wave systems, specifically for beam tracking and other things. Okay, these are the things that we are going to do in the next class. Okay, so next 2 classes, I think we'll take 2 or 3 classes. It will take for us to understand this whole SSP part. Okay, so I'm going to stop now. So thanks everyone. Thank you.
Thank you. Thank you.